And I am going to record the session, y'all. So let's see. Let me come back to this. Okay. So let's get rid of that real quick. Okay, so let's see. Oh, what I want to do. Tell you what. Let me try something real quick, y'all. We do this over here, this over here. I want to get you to know y'all's names and stuff. So, and I know it's hard to put a name to a face because we're all messed up and everything. But hello, I have some extra masks up here if you want one in case you do, or he's got one for you too. Okay, yeah. Let's see. Give me 1 second, y'all. Let me try something real quick. Summary class lists. Where's Calculus 1? This is us right here. Okay, so guys, I'm just going to go through the roster. I just want to make sure that I get to know everybody. Let's see. Some of you already know. Some of you I don't. Let's see. Brittany, is Brittany here with us today? Brittany, there you are. I see you. Julio? Julio is not here. I don't know if Julio, if he's online or not. Let me try something here. Let's see, everyone. Let me try this. Here we go. Nolan, Linda's here. Okay. All right. I'll just checking to see. Okay. Matthew here? No Matthew. Luciano, not here either. Let's see. Hello. What's your name? Sorry? Matias Lopez. Okay, I got you. Luis is not here either. Matias is here. Angela's right here. Good to have you. Jennifer's right here. Good to have you too. Uriel, we got Uriel here today? No. Alexis, no Alexis. Noel's online with us. Steve here. Steve, how you doing, Steve? Linda's online with us too. John is right here. And Luisa, is that you back there? There you are. Good to have you back. So some of y'all, I know y'all from last semester, y'all were in my pre-cal class. Some of you, this is our first time together. So guys, let me ask you a question before we get started. And Linda and Noel, this is for y'all too who are watching online. How have the videos been? Videos been helpful? Yeah? Pretty straightforward? When you're doing the homework, there's nothing like, oh my God, we never talked about this or anything like that. It seems like what I'm really trying to do, y'all, is making sure that whatever I'm lecturing on is something that, we'll put it this way, whatever you see in the homework, I want to make sure that I lecture on it. You know what I mean? That I don't want you to come across a problem. You're like, hey, time out, sir. We didn't, what are we supposed to do here? We didn't talk about this. Okay. So I'm really trying to make sure everything is very straightforward, y'all. Let's see, guys, a couple things I'm going to keep doing. I'm going to put it from the student preview so you guys can see, looks like from your perspective. Oh, and then we'll get started doing what we got to do. Okay, so obviously you've been coming to the weekly activities folder. So here's our week 3. Okay, so this is what we're going to be doing this week, y'all. So let's see. This is all the good stuff about, coming in or whatever. So let's see. Today, y'all, I'm going to go over 2.5 and I'm going to start 3.1. Our class is from 12:30 until 2:50. So we're here, like over 2 hours, right? Are we ever going to be here the entire time? It's possible, but I'm not the kind of professor that's going to say, hey, look, it's 2:30. You still have 20 minutes. You can't leave yet. I'm not, whenever we're done, we're done. Okay. So we're done at 2 o'clock. We're done at 2 o'clock. I'm sorry? Yeah. Yeah. No, it doesn't work that way, right? And guys, I'm never going to keep you past 2:50. You know what I mean? That doesn't make sense to me. So anyway, today we will cover 2.5. I'm not going to cover all of 3.1. I'm going to stop. We're probably going to finish before the 2:50 comes around, but I'm just trying to pace it. I don't want to give, I don't want to give y'all more than we really need to do, right? And I've kind of made a calendar for the class, and actually this week we're actually getting a little bit ahead, but I'd rather us get a little bit ahead than at the last, 2 weeks, let's try to cram all this stuff in, right? So I'm just trying to pace it. And then Wednesday, y'all, we'll finish up 3.1 and we'll do 3.2, okay? So today, y'all, the homework for 2.5 will be open. What I'm really trying to do is give you a week to do each assignment. So like today, 2.5 is going to be open. It's due by next Monday at midnight. I think I put that right here. Yeah. So homework for 2.5 is due a week from today by 11:59, right? 3.1, that homework will open up today too, but because we're not going to do all of 3.1, that homework and then the stuff that we're going to do on Wednesday, 3.2, that'll be due next Wednesday. Does that make sense? So you basically got a week to get each assignment done, right? So if we start 2.5 today and if we finish it, you got a week to get it done. Even though we'll start 3.1 today, since we're not going to finish it until Wednesday, it'll be due a week from this Wednesday. And then let's see. We're all going to have there's going to be a quiz, y'all. The quiz has, let's see, is due next Wednesday. It'll open up today though, but I'm just giving you a couple extra days. It has 10 questions that I took directly from the homework from 2.1 to 2.5. So we're using this thing called My Open Math, right? It's free, you don't have to pay for it. Part of it is, you know, like anything that's free, it's kind of like the trial version, you know what I mean? You don't get commercials or anything, but it's just a little more limited. But one of the things that I can do is when I make the assignment, I can pick questions directly from other assignments. So that's what I did. When I made the homework, the quiz for chapter 2, I went and I made sure that I asked questions that I had already assigned in 2.1, 2.2. So everything you're going to see on the quiz, you've already seen the problems. You're just doing a new version of it, right? Again, here's our YouTube playlist, right? So, and then you should see here, here's the homework for 2.5. And again, it's due on the 7th. 3.1 is not due until next Wednesday, 3.2 next Wednesday, and the quiz next Wednesday. And this one here, and this one here, they should be open already, okay? 3.2 won't open up until Wednesday, guys. The other thing I did, I just put a link here also for our YouTube playlist, so you don't actually have to go to each of the folders to look for our YouTube playlist. I just put a link for it right here. You can bookmark it if you want to, whatever it happens to be, okay? All right, so anyway, so far we're doing okay? Everything's been working? Okay, just checking with you guys. All right, so today, y'all, what we're gonna do is we're gonna talk about something called the precise definition of a limit. And I'm gonna tell y'all a little story of when I took Calculus 1. It was called differential calculus back then. There used to be, instead of a 4-hour class, it was a 3-hour class. So we had to take 4 calculus classes instead of 3. And the professor I had, after about 6 weeks, they replaced him because he had a little problem with, and he would come into class with a coffee mug, and my class was at 5 something in the afternoon, and it wasn't coffee. And but a couple things I remember for him was this one section, I absolutely hated it. I hated it, okay? And I'm going to tell you why I hate it, but we'll go through it and we'll kind of figure out what this stuff means. All right, so 2.5 is the precise definition of a limit. So we're going to talk about something called the epsilon delta definition of a limit. We're going to apply the epsilon definition to find the limit of a function. We're going to describe the epsilon delta definition of one-sided limits and infinite limits, and use the epsilon delta definition to prove limit laws. Okay, so let's get to this part right here where it says quantifying closeness. So before stating the formal definition limit, we're going to talk about a few preliminary ideas. Recall that the distance between two numbers on a number line is given by the absolute value of a minus b, right? Absolute value, y'all remember, you probably the first time you heard absolute value was probably sometime in junior high, maybe 6th, 7th, 8th grade. And the one thing we all remember about absolute value was never going to be negative, because the absolute value was talking about the distance, right? So I said, how far is it from where I'm sitting to where Luisa's sitting? We might say something like, oh, I don't know, 20 feet. Well, how far is it from when she's sitting to where I am? It's still 20 feet, right? Distance is never negative. The absolute value ensures that we're not going to get a negative number, right? Okay. So now it says the statement of the absolute value of f of x minus L is less than, that little funny looking E is what we call epsilon. Okay, it's just a Greek letter. May be interpreted as the distance between f of x and L is less than E. Okay, so it's just referring to the distance. How far whatever that distance epsilon is, the distance between those two numbers is smaller than that. Okay. Now look at the second statement. It says the statement 0 is less than x minus a, and absolute value is less than, that's delta, that kind of funny looking kind of looks like a a fancy S. That's okay. That's capital delta. So just like our alphabet, we got capital letters, lowercase. So do the Greek letters. Yeah. We don't have a monopoly on capital letters. They have them too. You know.
Is it different kinds of delta in math, or is it?
No, it's just it. Well,
because I know math is very specific about this stuff sometimes.
yeah, you're probably going to use. I've never seen where they use the capital like the triangle. You know what I mean? I've never seen it in terms of this definition. Okay, so it says may be interpreted as x is not equal to a, and the distance between x and a is less than delta. Okay, so number one, why is x not equal to a? Because it's telling me that the distance is going to be positive, but it's going to be smaller than some number delta. Okay. All right, and it's also important to look at the following equivalence for absolute values. So the distance of f of x minus L is less than epsilon is equivalent to this statement. This just tells me that my f of x value is going to be somewhere between L minus epsilon and L plus epsilon. Have you guys ever heard of the term tolerance? So if I don't know if anybody here is planning on going on like mechanical engineering, but when you're doing manufacturing, and that's something they do in mechanical engineering, say you're making, I don't know, you have a machine that's making bolts, right? And the bolt needs to be, say, 1 centimeter in length. Well, every bolt is not going to be exactly 1 centimeter in length. Some are going to be a little bit longer, some are going to be a little bit shorter, right? But that's what we call a tolerance. It's okay for them to be a little bit longer, a little bit shorter, as long as they're not longer than this amount, and as long as they're not shorter than that amount. Does that make sense? So this is what I highlighted over here or put in the red box shelf. That's basically what that's telling you. And this, we can state the formal epsilon delta definition of a limit. So it says, let f of x be defined for all x not equal to a over an open interval containing a. Let L be a real number. Then the limit as x approaches a of f of x is equal to L. If for every positive number epsilon, because epsilon is a positive number, then we can find a positive number called delta, so that if the distance between x and a is smaller than delta, but it's still positive, then the distance between f of x minus L is going to be smaller than epsilon. And it says this definition may seem rather complex from a mathematical point of view, but it becomes easier to understand if we break it down phrase by phrase. Okay, so look what it says right here. For every epsilon that's positive, there exists, we call an existential qualifier, delta, that's also positive, so that if the distance between x minus a is less than delta, then the distance between f of x minus L is less than epsilon. Okay, so
the function
minus the limit. Yeah. And that's what this part kind of breaks down right here, right? They're just kind of breaking it down into, breaking down the translation. But I want to kind of show you the graph, because the graph is going to help me figure this thing out. Okay. So let's take a look right here. So it says the graphs show possible values of delta giving smaller choices of epsilon. Okay, so I'm just going to focus on, say, one of them. Let me focus on the one in the middle. Okay, so the distance, y'all, between here and here is my epsilon. Okay, remember, this is my limit. This is the value of L, right? So if I have, and I want you to think about what my epsilon is. My epsilon is going to be a number that's positive, but the idea is it's going to be small. Remember what I said earlier, we're making bolts and it's supposed to be 1 centimeter in length. It's okay for it to be a little bit bigger or a little bit smaller. What do I mean by a little bit? Like, 0.01 of a centimeter, or what about smaller, 0.01 of a centimeter, right? Well, look, I'm making 1 centimeter bolts. This one is 2 centimeters. Is that good enough? No, it isn't. That's way too big, right? it can be a little bit bigger, a little bit smaller. Think of you're making bolts for your car. It can be a little bit bigger or smaller, everything's going to be fine. But if it's that much bigger, it's just not going to work, right? It's not going to fit where it needs to fit. Okay, so the idea is if I have this little kind of window right here, then I can find a little window in here. The values of these are my deltas because now I have this piece right here, this value here, y'all, would be A, oops, come on, pen. This value here would be A minus delta, and this value here would be A plus delta. The idea is if I pick a value, say right here, if I were to go up and hit my graph, I'm still going to fall in that little window on the other side. That's basically all the limit is telling me, is that if I pick numbers really close to my alpha, to my A, then I'm going to find values really close to my limit L. That's what the formal definition basically tells me. And the idea is the smaller that I make this part right here, if I make those epsilon values even smaller, then what's going to happen is that my delta values are going to get smaller too, right? So if I want that tolerance to be even smaller, then I got to make sure that I'm more precise. Okay. All right. So now I'm going to show you how we can actually apply some of this business here. Okay, so what we have here says, show how we can use the definition to prove a statement about the limit of a specific function at a specified value. Okay, so we're going to do the limit thing here, y'all. Okay, so remember the first thing, number one, we're going to let epsilon be greater than 0, right? The first thing is that little window close to my limit has to be a positive number, but the idea is it's going to be small, okay? So the formal definition says there's going to be a delta that's going to be positive so that if f of x minus L is less than epsilon, then x minus A is less than delta. Actually, it should be the other way around. My bad. Let me fix this, y'all. Okay. Okay, so the way we're going to do this, y'all, this is basically going to be almost like straight plug and chug, like a substitution type problem. Okay. So what we're actually going to start with, y'all, we're going to start with this part right here. So I'm going to do absolute value. What is our function in this particular example? What's the expression we're looking at? 2x plus 1, right? So we're going to put 2x plus 1 minus L. What is my limit in this case? It's supposed to be equal to what number? The limit's going to be equal to 3, right? Okay. We're going to set that smaller than epsilon. Okay. Now, what we're going to do, y'all, is we're going to manipulate this piece right here. Okay. So let's see if we can do that. So look, we're going to go like this. 2x, let's see, plus 1 minus 3 is a minus 2 is less than epsilon. Okay. Can I factor anything out of here? 2. Okay. Now, I'm going to ask you all a question. If I wanted to get this absolute value of x minus 1 by itself, how would I get rid of that 2? Divided by 2. Okay. Now, the whole reason why I was doing that is I want you to look at this piece right up here at the very top. Do you see where it says, I just circled it in green? Oh, you know what, guys? Let me check something real quick.
Checking the recording?
Yes, we are. Good. That would have made me real nervous. Okay, we're good. Let's come back here. Okay. Guys, I'm going to ask you all to do me a favor. Those of you who come to class, just because it happens sometimes, remind me, please, sir, hit record. Okay, so I can make sure I'm recording. I want to make sure, okay? I'm usually pretty good about it, but every now and then it happens. Okay, so let's take a look what I wrote right here in the green, y'all. I'm gonna write that part in the green. X minus, what is my A in this case? We're taking the limit as x approaches what number? As x approaches 1, right? And that's supposed to be smaller than delta, right? Now, do you see how we started off with this piece, how we ended up with this piece right here? Doesn't this right here look exactly like that right there? So then what we do is we're going to say, look, we know that epsilon is positive. We're going to let delta be equal to, in this case, what we ended up with was epsilon over 2. Okay, why? Because since this piece here and this piece here match up, we're going to say let this piece here and that piece there match up as well. Okay, now basically what we're doing, y'all, is we kind of worked backwards so we could find our value of delta. In all these problems, the objective is going to be, can I find my value of delta? Now that we've done that, we're basically going to rewrite the problem in kind of the correct order. So the way we're going to, and this is just part of the problem, okay? So the way we're going to do this now, y'all, we're going to say, number 1, let epsilon be greater than 0, and let delta be equal to epsilon over 2. Number 2, we're going to say the distance between x minus 1, because that was my value of A right here, is going to be equal to epsilon over 2. Okay. And then basically what we're going to do, y'all, is we're going to say step number 3, we're going to work our way backwards. We're just going to copy the steps in the reverse order. So look, if I'm right here, what's the next thing? Oh, look, multiply this by 2. X minus 1 is less than epsilon. Distribute that 2 inside so that we have 2x minus 2 is less than epsilon. Rewrite the inside so that it looks like this. 2x plus 1 minus 3 is less than epsilon. And then the last step is we're going to say 2x minus 1 is my f of x. The 3 is my L, is less than epsilon. And now you're done. So really what we're doing is we're going to assert what it is we're trying to prove. We're going to see, can we make that happen? And when we do that, can we basically rewrite the f of x minus L so that it looks like an x minus A? And then once you have that, you just write it in reverse. Okay. Oh, sorry, John. Come back. Guys, also, as I'm doing this, if I ever go too fast or something, just let me know. Tell me, sir, can you slow it down a little bit? I'm more than happy to do that, okay? That's all you're doing. That's all you're doing, yeah. So look, let me go ahead and scroll over here, y'all. So look, it says problem solving. Okay, so look, let's begin the proof with the following statement. Let epsilon be greater than 0. That's the first thing we did. We need to find a delta, a value for delta. After we've obtained the value, we can fill in the blank of our choice. Choose delta equal to, what did we do in the problem before? We said delta was like something like epsilon over 2, right? And then we're going to kind of start and we're going to go through and then we're done, okay? So look, this is how, like this, y'all, I just copied this directly from the PDF version of the book. And so look how they do this. So it says complete the proof showing the limit as x approaches -1. 4x plus 1 is equal to -3 by filling in the blanks. So let's take a look. Look how they did this. They said, look, let epsilon be greater than 0. We're going to choose a value of delta. Okay. So assume that x minus a negative 1 is less than delta, or equivalently, x minus a negative 1 is the same thing as x plus 1. Absolute value is less than delta. So look what they're doing here. This is my f of x, right? This is my L. So they're rewriting it. Here is my absolute value of 4 times x minus 1 is less than 4 delta. Okay, so look what they're saying. In this case, they're saying delta is going to be equal to epsilon over 4. And then how do we start this off? The same way we did our problem. Does that make sense? So whatever it is you're trying to prove, you're going to set it that equal to that epsilon, and then you're basically rewriting the f of x minus L so that it looks like your x minus a. Once you have that x minus a on one side, whatever expression you have for your epsilon, whether it's like epsilon over 4 or epsilon minus 1, whatever it is, that's going to be your delta. Okay. Okay, so look, let's see if we can do this problem. We're going to do it the same way we did the other ones. Okay, so we're going to kind of do our work first, right? Our scratch work. So I'm going to do this in purple or pink, whatever this is. This is my scratch. Okay, so we know that epsilon is positive, right? And we want to write our absolute value of f of x minus L so that it is less than epsilon. Okay. So in this case, what is our f of x, y'all? Yeah, 3x minus 2 minus, what is the limit supposed to be equal to? What's the value of my L? No, the value of my L, though. So the 2, y'all, this right here, just to give you a heads up, that's my A. This one here is my L. Okay, good. It's okay. We'll figure this out. Okay, so look, the limit is 4, and that's supposed to be less than epsilon, right? Again, y'all, all we're going to do, we're going to rewrite this thing, right? So look, we're going to come back over here. We're going to say 3x minus 2 minus 4 minus 6 less than epsilon. Okay. And let's see. I'm going to factor out the 3. That's going to give me x minus 2 is less than epsilon. Okay. We can take that 3 outside of the absolute value without changing it because 3 is a positive number, right? And then we can divide everything by 3 so that we can get x minus 2 is less than epsilon over 3, right? Okay. Now that we have that, the first thing, y'all, we're going to do, the first part is always let epsilon be greater than 0. Okay. Now, what do you think we want our delta to be equal to? Yeah, the little epsilon over 3, right? Okay. So, y'all, just to give you a little reminder here, just so that we know what it is we're trying to do, okay? Reminder, we want to show that if x minus a is less than delta, that's going to tell me that f of x minus L is less than epsilon, okay? So this is just kind of like my little reminder. So I know where it is I'm trying to go with this thing, okay? So let me ask you a question. If we have right here x minus a is less than delta, what is my a? What did we say our a was again in this problem? 2. So look right here. We're going to write x minus 2 is less than, now what are we calling delta again? Epsilon over 3, right? So I'm going to put right here, epsilon over 3. Okay, and then right here, y'all, I'm going to write it like this. I'm going to put f of x minus L, okay? And so look, let's do it like this. What did we say our f of x was? It was 3x minus 2 minus 4, right? Which is equal to 3x minus 6, right? which is equal to, let's see, 3 times the absolute value of x minus 2, right? Which is less than epsilon over 3. But I need to multiply this guy by 3 because of that 3 over there. And isn't that equal to epsilon, which is what we have kind of right there? You just didn't give me enough room to write it in. So look, all I'm doing here, y'all, this 3x minus 6, I'm putting is the same thing as that 3 times x minus 2. But because we know that this piece right here is basically this piece right here, if I have this 3 here, I got to write that 3 right there también. Right? Yeah. So let me clean this mess up because I'm trying to figure out the easiest way to kind of explain this for us. Okay, so you agree with me that this part right here is the same thing as 3 times x minus 2? Okay. Now, do you see how this piece right here, isn't that the same as that piece right there? Okay, and let me do this. Wasn't that part right here less than what? Epsilon over 3? But see, this piece right here was less than epsilon over 3, but because I have that 3 in front here, don't I need to put a 3 over there as well? So that this piece here and that piece there can be the same? And then won't these 3's cancel out to give me my epsilon? Yeah, because a 3 on the top and a 3 on the bottom will cancel each other out, right? You multiply by 3, divide by 3, you kind of get the same thing. Does that make sense? Good, good. How did I get the 3? Oh. Yeah, yeah. Oh, remember, my number 4 was right there, right? So the fact that I'm using this 3 doesn't have anything to do with the 4, though. You know what I mean? The fact that I'm using the 3 was because we had an epsilon over 3 here. Does that make any sense, or did I lose you? Lost you a little bit? Okay, it's okay. It's okay. Look, we're going to figure this out. Huh?
Why did we get to isolate epsilon?
Because the idea says, look, if, yeah, the idea says, look, if f of x minus L is less than, I'm sorry, if x minus a is less than delta, then f of x minus L is less than epsilon, right? Let me see if I can write it a better way. Let me try this, and you tell me if this makes more sense, y'all. Okay, so, yeah. Yeah, so look, let's try it like this. Let's try it this way, and you tell me if this makes more sense. So, see how, let's go right here. Let's fill this blanks in. X minus 2 is less than epsilon over 3, right? Okay, so if I write this, x minus 2, and I multiply that by 3, would you agree with me that that would be equal to 3x minus 6? Okay. Would you agree with me that that would be equal to 3x minus 2 minus 4? Would that make sense? Okay. Would that be the same thing as f of x minus L? Because isn't this my f of x? And isn't 4 my L?
When you went from 3x minus 6 equals 3x equals 2, you only plug in the divided the 3 with the 6, not the 3x.
So from here, I multiplied the 3 to both of them, right? That's how I got this piece here. All I'm doing here is I'm breaking up that minus 6 into minus 2 and minus 4. Okay, and then isn't this piece here my f of x? And isn't this piece here my L? And then therefore, my limit exists. Is that better? That probably works better. Yeah, that probably works a whole lot better. Yeah.
Is this why you hated it, or we got not come to that part yet?
This is probably why I hated it. And to be honest, in all honesty with you guys,
Proofs in general, like,
as I went to grad school, I got really good at proofs. Like all the proof stuff, I was like great at it. The application stuff, and it took me a harder time. I had a harder time with that. But I'll be honest with you. In the entire time that I took calculus, what we did is we actually did the actual problems. So I hated doing this part because at the time I didn't necessarily see the relevance. Like, why am I going through all this stuff, right? If I know how to find limits, I understand, like when we came, I'm going to kind of pause back over here, y'all, and come back to this part, right? And I think this part makes sense in the sense of like, if I make, let me do this. If I make this window right here really small, right? Like remember what I said before, if I'm making bolts and I want them to be 1 centimeter in length, but my tolerance is going to be very small, meaning it can be 1 centimeter plus 0.01 and 1 centimeter minus 0.01, that means that I have to be very precise. I don't have a lot of wiggle room. I got to make sure that as I'm coming into my limit, that I'm taking smaller and smaller limits so that I end up in that 1.01 of a centimeter. That to me makes sense, and I understand that, and I think that part is really important. I think that's one of the most important parts of a limit. Actually doing the proofs to like do this kind of stuff, I don't particularly find it a whole lot relevant. So like I think in your quiz, guys, like I said, that quiz for chapter 2, if anything, you got one problem from 2.5. You know what I mean? I didn't put a ton from here just because, as we say in Spanish, pa qué, right? What for? Okay, so look, let's see if we got another one similar. Here we go. Okay, because this is the last problem here out of 2.5. Your homework for 2.5, guys, has like 4 problems in it too. It's not a lot. Okay, so let's take a look here. It says, while demonstrating the limit of, as x approaches 0, 4x plus 5 is equal to 5, with epsilon equal to 0.5, which of the following suffices? Okay, so we're going to do the formal definition again, right? We know that epsilon is greater than 0, right? Okay, remember who we're going to start off with, y'all. F of x minus L is less than epsilon. Okay, what is my f of x in this case? 4x plus 5. Perfect. What is my limit supposed to be equal to? Excellent. Good. I could have stayed home. You already know what to do. Now, guys, I want to show you something here. See how we have epsilon? What are they telling me epsilon is equal to? 0.5. So I'm going to put a 0.5 right there because they're giving us that value. Okay. Now, everybody agree that this is just going to become the absolute value of 4x because the 5s are going to cancel? Okay. And then we can pull out the 4 because it's okay to pull it outside the absolute value because it's positive anyway. And then if we were to divide everything here by 4, wouldn't we get the absolute value of x is less than, I don't know, I'm going to grab my calculator real quick, and I'm going to ask myself, turn it on. What is 0.5 divided by 4? 1.25, or 0.125, I'm sorry. Okay, now, remember how we would do this part here? X minus a is less than delta. Do you know what my a is in this problem? 0, very good. So x minus 0 is less than delta, right? Okay, let me ask you a question, y'all. Can I rewrite this guy down here in the green as x minus 0 is less than 0.125? Yeah? Okay, so then wouldn't we say delta, bless you, is going to be 0.125? Because we just rewrote this guy right here so that it looked like x minus 0. And if that's delta, then delta's 0.125. Okay. The idea here, y'all, is what we're looking for is delta can be this value or it can be smaller. So I'm not just going to pick the 0.125. I can pick any number that is smaller than or equal to 0.125. So look, I'm going to zoom in right here, right? Delta is 0.125. So I can choose that one, okay? What other values here, y'all, are smaller than 0.125? The next one, okay, boom. What about 0.25? Can I pick that one? No. The last one? Is this smaller than 0.125? There we go. And that's what you're doing. You're just picking numbers that are small. They're smaller than or equal to 0.125. Those are from the list that we have, right? Obviously, there's a lot of numbers that are smaller. Okay, guys, we're going to run into some problems because I forgot my power cord today. But I'm going to keep going. Wherever we stop is where we stop, okay? But guys, this here, what we just did, that's 2.5. Okay, that's 2.5. I'm going to keep going, but I'm going to show you something real quick like, let's see, go to content. I'm going to pull up my homework from 2.5 if it allows me to do it. Is it allowing me to do it?
Launch.
Oh, okay. Yeah, this is my first time using it because I've always used like Alex, my math lab, 5 questions, okay? So start, okay. We can figure out how to do it, right? It should let me go to question 2, right? Without having to do anything. Question 2. Isn't this problem like the one we just did? Okay. Question 3, it's just a video question, right? So it's pretty easy. Okay. Which of the following is the most correct interpretation as the limit as x approaches 3 of f of x is equal to 8? Okay, remember what the limit means. So remember, guys, in I want to say it was 2.4, we talked about continuity. Remember, continuity is a little different from limit. Continuity means the limit exists, the function evaluated at that value exists, and they're the same, right? So there's a difference between continuity and the limit. So we saw in 2.4 that you could have the limit when we looked at the graph. It's coming in, there's a value, but there's a hole at the graph, right? And then the point was either up here or down here. The limit still exists, but the function wasn't continuous, right? Okay, so let me ask you a question. If it says, which of the following is the most correct interpretation of the limit as x approaches 3 of f of x is equal to 8, would you say the first one, is that the most correct definition? No, because now we're already talking about continuity, okay? When x is equal to 3, the outputs of f of x get closer to 8. That sounds a little bit better in the sense that we're getting closer to what? To the limit, right? Look at the third one. When x gets closer to 3, the output of f of x gets closer to 8. Does that sound better or does that sound worse?
No, it says
Is the output of f of x is 8? Oh, sorry, there we go. And then look at the fourth one. As x gets closer to 3, the outputs of f of x get closer to 8. Which one sounds the best to you? The last one, right? So we'd submit it. Hey, we're doing good, right? Isn't this just like the last one we did too? Okay. So again, guys, you can see the problems that I'm doing in the notes directly correlate to what you're going to see, okay? That's always been my teaching style. I don't want to give you anything that, hey, we didn't talk about this. What are we doing it for, okay? All right, so let's keep working a little bit, y'all. We're going to work until my battery dies or until I get to the point that I want to get, which is, let me tell you.
We don't have to ask you to go to the bathroom, right? You just
Yeah. If y'all need to go to the restroom, guys, y'all please go ahead and go, okay? Y'all go. At the end of the hall, and then take a right where the doorway is. I think the men's is on one side, the women's on the other. But you're basically you're gonna get to the bathroom, going to the outside of the building, just like the way we came in through here. Okay, so let's do a little bit more of let's do some 3.1, y'all, and hopefully my battery lasts a little bit longer. And we'll continue on Wednesday, guys. 3.2 is not a long section, so wherever we end, we'll be able to do both of them on Wednesday, okay? All right, so 3.1, defining the derivative, recognize the meaning of the tangent to a curve at a point, calculate the slope of a tangent line, identify the derivative as the limits of a difference quotient, calculate the velocity as a rate of change, explain the difference between average velocity and instantaneous velocity, and estimate the derivative from a table of values. All right, I'm not going to go into the whole history with Newton and Leibniz because that is not my thing.
Your own professor.
My old professor. Oh, okay.